Hello and welcome to Tonight at 8 from the RSGB. Many people agree that 2025 technology is wonderful, with sophisticated but relatively inexpensive electronics used in so many products, including, of course, amateur radio equipment. This might leave you feeling that you could not possibly make anything of your own to compare, but the art of construction is alive and well, and in addition to enabling you to make something do exactly what you want it to do, it can also give you that uniquely satisfying feeling that you made it yourself. Tonight's guest is Lee Aldridge, G4EJB, who has spent many years designing and building projects, as well as encouraging amateurs to make things, both through magazine articles and as a former editor of the RSGB's RadCom Basics publication. Tonight he's not only going to show you various different ways on how to construct your own projects, but is also going to give useful tips and techniques on fault finding basic electronics. So welcome to Tonight at 8, Lee. Can you give us a quick overview of what you'll be covering tonight?
Yes, certainly, David. The idea of tonight is aimed at newcomers who would just like to know where to start with construction. They may well have not come from a technical background, and there may be a number of people about who have built things and probably haven't got things to work, or again, because of the lack of technical knowledge, would just love to know, what do I do to get this thing going? So that's what I'm aiming at tonight. Thank you.
Lovely. Well, we're really looking forward to it. If you're watching this on Monday, the 3rd of February, then this is live. And you can ask questions or make comments on either YouTube chat or BATC messaging at any time during the presentation or straight afterwards. Please include your first name and call sign if you have one within every message. And note that you can make this video stream fill your screen on most devices, usually by double clicking on the picture or pressing the full screen button. So let's find out more about basic electronics and fault finding with Lee.
Thank you very much, David. It's very nice to be with you all this evening. I hope you can hear me perfectly okay. What I'm going to do is just have a quick bit of an overview so you know what we're actually going to cover. We're going to have a brief look at various construction methods, consider a few positives and some shortcomings, having built something, what to do if it doesn't work, basic circuit appreciation, and I will keep it as basic as I can, I promise. We then have a look at a bit of simple fault finding using just a digital multimeter, nothing more than that. And then hopefully by about 12 o'clock tonight, there'll be enough time for a few questions. Now, I'm only pulling your leg. I hope to finish well before then. Right, so a few prerequisites with construction or even building anything. Somewhere where you can safely put a project together. The kitchen table has been used many times over by people, and it's not always favoured by other members of the household. I will say to you, the reason why I bring it up is it will just save you problems, or it just makes it a lot easier to build something, less chance of risks of things going wrong. So try and get a little space put aside where you can actually do this type of work. The necessary tools, I brought a few along which I prepared earlier. Let me just see if I can pull a few of these out to show you. You do not need to spend a fortune on tools to do this type of work. I certainly haven't. I've got some tools that probably, some of them may be, say 30, 40 years old, and some of them still doing sterling service. Simple things like side cutters, a sharp pair. It's a very good idea. These are very cheap side cutters, but if you treat them carefully, they're going to do a really fine job for you for a number of years, like that pair have for me. Good lighting. I know about this, and probably 20, 30 years ago, I could have probably got away with the type of lighting I've got this evening. But the reality is now that much older, I need as much light as I can get just to be able to see things in detail. I've shown a little picture on here of one of my setups, which I had when we were up in Shropshire. And this was made with a garden potting table. Potting table, that was it. Put a piece of vinyl across it and then built some shelves to go across. And as you can see, a lot of stuff on there, but that is the reality of how I actually work. Good quality components. And if applicable, we'll get onto that one, the clean circuit board. The components of which I've shown on there are basically wire-ended. That's the type of stuff I work with. Occasionally I will get excited enough to find some surface mounted, but I still prefer if I can use these wire-ended ones because I can see it and it works really well for me. Next to it is a little piece of copper clad board, which hopefully, yes, I'm just holding up there, we may get a bit of light on it. And it's just copper clad on one side and plain on the other. It's available from all over the globe, and there are varying qualities of it. So be aware of some of the really cheap ones. The copper clad can be very, very thin indeed, but it's still usable for amateur projects. Right, that's that one goes down there. Good soldering skills. I cannot overemphasize that one of the biggest problems there's been for years is people being able to solder well. And that's not just in amateur circles, even professionally. It's about getting good quality soldering done and looked at. Soldering irons, you can spend a fortune on them, without a doubt. And there's very good reason, particularly professionally. You want those irons to work for a lot of hours per week for many years to come, and obviously be able to keep supporting them. But I have to tell you, you might just about see this. This is one of the soldering irons I'm still using from the 1980s. Now, I'm not recommending this to you, apart from a couple of factors about it. It is that it's a very slimline iron. It was made by Antex, but some of the things of which aren't so good about it is it hasn't got heat-resistant cable. It's 240 volt to the actual element, even though it's a ceramic element, and that's not particularly a good idea when you're working with stuff that could be static sensitive. It's also earth, so it's also an issue with static sensitive. So one of the things I will say to you is my other soldering iron only cost me about £8 or £9, which is temperature controlled, but it also is a very good wide generator of interference. So if you're thinking of listening to a radio while you're using it, forget it. When I can afford it, I will replace both of these irons with something a little bit safer. I like the idea of a low voltage iron and obviously the temperature control. I think the best advice I can give is talk to people in clubs, other radio amateurs, and say, what are the types of irons which are decent these days to use? Obviously, professionally you use things like Weller irons and some of the Antex and various other ones. They're really, really good irons. And of course, there is a little bit of a price, but they are very good. And here we go to the one final thing I'll mention about a few prerequisites. Good enough eyesight. As I say, years ago, I didn't need these particular things I'm wearing now. I could see surface mount, and probably that has also contributed to some of the problems I've got with my eyesight now. But I do notice when I'm working with people that they are struggling with eyesight. And it's one of these things I say to you, go and regularly get it checked. You can, of course, spend a lot of money on it. I have to tell you, and I'm not going to advertise where, but one of the supermarkets has got its own chain of opticians, and they do 2 pairs of varifocals. I think they would cost me about £130. Are they as good as other varifocals? They're not bad. That's what I could afford to do. But one pair I've got are the ones that I'm wearing tonight, which are office pair. So that means it was ideally built for working with a laptop and obviously even stuff closer. So these just make it a little bit more relaxing for your eyes and for your head, trying to actually focus on things. Right, let's move on a little bit. Construction methods. That's what you'd like to know a little bit about. If I was going to recommend a construction method for people to begin with, I would certainly say kits. And the reason for it is a lot of the work has been done for you. I've shown in this particular picture 3 old kits. One which has been around for a number of years, which is at the top from Tim Walford. The other one would have been one which was very popular in the 80s and 90s, which were Howe Electronics. And then there's another one now, which is from Hellman, not Hellman, the mayonnaise people, from Hellman, and that is just an audio amplifier. And that, believe it or not, is still available. Now you can see different complexities of construction. And if I was starting construction, I would obviously say something simple and hopefully something that is going to be of some use to you. An audio amplifier may well be a starting point, but it doesn't just have to be radio orientated. Now, these particular boards, I brought a similar board in, and I hope I can get this about right. If I can hold it steady, there is a board, thank you, a board which actually shows where components are mounted. I used to notice silk screening many years ago. Components which are wire-ended, let me just pull that one back out. Just literally go through the holes on the board. I'm going to put it in, even in this light, I hope. You can see how good my eyesight is now. That resistor, which I will just hold to the side so you can see there. There you go. There's a resistor. I'm going to just push it through the board and then go to the other side, and I am just going to bend over so far the leads. There's a wire-ended leads there. That is holding it securely in place. Now, classically, you would be told this is the point where you solder it, and then when you've soldered it, you would then do what we call cropping the wires with a pair of side cutters, not leaving a long length of wire shown. And that is a standard push through the board means of construction. As time has moved on and surface mount components have come to the fore, that has become a little bit of an issue for people wanting to produce kits and sell them to people. And they've come up with ingenious methods for saying, right, we'll actually put the surface mounted components on the board and leave you to do the rest of the wire-ended components through. And I think that is an absolute brilliant way of doing things. I really do. If anyone wants to know what that thing wrapped around that one particular board is, that's the G4EJB method of getting better frequency stability in a whisper transmitter. I'll answer questions about that another time. I think that's a Kanga 40-meter transceiver, which was shown in RadCom not so long ago. What I've also shown is a slightly different take on construction from a friend of mine. He decided to get hold of kits from the Far East, of which had very poor instructions with them, and anglicized instructions, so that people could build just something straightforward that would do something for them. His idea is get people building something, and I think it's a brilliant ethos. I want to come back to the reason for kits. I mentioned to you earlier, is all the work's done, printed circuit boards done, and also you probably will get some very good instructions from the majority of people, be it on paper or online, whatever it takes to actually get the information to you. So the point is they put all the hard work in. All you've got to do is basically follow the instructions properly, methodically, and they want this to work for you, because the theory being is you'll probably go and buy another one or build something else another day. I'm going to step back in time now. Yeah, a bit like me. And what I'm showing you now is what was perforated board from probably the 1960s, or somebody will probably tell me different, but I certainly remember it by the time I was playing with stuff like this in the 70s. And the idea of this particular stuff is you just put components, again, wire-ended components in this case, just straight through the board. Again, bend the leads over. And if you look at the underside, the wires are then bent over and then soldered to whatever point is required to make a circuit. Now, the big difference, why I've just brought this up, is the difference between using this type of board and a number of other forms of construction. I have seen people build kits who have little idea on how to read circuit diagrams, or just haven't done that type of thing before. I have seen them build complete transceivers with, very little knowledge, because the instructions were that good and they just went through it step by step. And I commend that type of work. It's brilliant. But as I say, this type of work now requires you to understand, circuit diagram. Where do I connect this to there? And it's a case of putting components in the one side, going over the side and going, right, that's where it's got to go on that other side. That's the theory. And just after perf board or perforated board appeared, you then came out with, this is only a small piece of board. It's the only piece I could find this evening. This is strip board, as I'm showing in the actual photos. And this was again developed to make it easier to fabricate and develop very simple boards, again with ICs. There's one thing I didn't mention. I will wander all over the place, as is my want. Both of these boards really came to fruition with DIL and SIL ICs, because they've got a pitch of 0.1 of an inch, which is exactly what IC pins were of that era. These strip boards were brought out as another means to actually join other components up. It was a little bit sturdier in some ways to just using the perf board. There are some pluses and minuses to it, which I will go into. If you look at the little photo in the center, you will see probably what is, it certainly looks like it to me, is the underside of where an IC has actually been mounted on the board and soldered up. And if you can get enough resolution, you'll probably find that there's some holes being drilled so that the actual copper tracks are not joined together. Right. So a little bit of drilling is required to actually separate different tracks. I promise you, nearly everything that I have built, I have missed one. Hence the reason why you have to be very methodical about checking your boards when you're building with this, because you can so easily say, right, I've used the same strip twice, but I need to have made a break within it. Another downside of this board is it's not really built for a great deal of RF, because these are copper strips that are running parallel. And two copper strips running parallel look very much like a capacitor to me. So that means this board in itself can actually affect the way that RF components or RF conscious components work. But the thing is, that doesn't stop people building with it, including myself. And I have built a number of little radios on this board despite the shortcomings of it. The one board of which I've actually got to illustrate there is actually just a semi-break-in board used in a little transmitter receiver. It means that when I press the CW key, there, or Morse key I should say, it'll go over from receive to transmit and then come back again. So there's RF on that board across a relay, and obviously it's being switched by a transistor, etc. Now, just a closer look, some more downsides of this particular means of construction. When you're soldering, and I make no apologies for the type of welding that you can see on the back of this board. It's just the way it typically works out. Some of the issues you get with this board is it's very easy to get either a whisker or a slither or even a lump of solder across two tracks. So you probably need a thin-tipped iron to work with it. But one of the little tricks that I also do when I've built like this is I carefully run a precision screwdriver, not a knife, precision screwdriver along the actual insulated part of the gaps between the tracks, I should say. So the reason I put a little red ring around that part there was this is where somebody not very far away from this pair of earpieces decided to remove a component. And as this board was built for probably one or two uses, it's very, very easily, particularly with cheaper board, to get the soldering iron on there and rip a piece of track out. So be aware with this type of construction. It's a bit fiddly in some ways. You've just got to make certain you don't get wires over, keep it clean and make certain that there's nothing going to short between boards, between the two tracks, I should say. Again, another shortcoming of this particular construction is current. It's how much current can it take? Well, also it's to do partly with the thickness of the board, of the actual copper clad, I should say, on the board, but those holes drilled are going to limit the amount of current that can actually run along that track. So a way around it, if you are looking to run more than a few milliamps or 100 milliamps or whatever it is these days, people will tell you to run, then I run a piece of wire across the top, or just use solder to actually increase the capacity of the track. Those are some of the little tricks you can get up to with it. And on to the more recent one on the block, which is this, what was called prototype PCB board. And I quite like this, even though I haven't really started building with it. But I do like the fact that it's double-sided, so that, or the one that I have bought is double-sided, so I can put the components through, like we've done in the last two examples. Excuse me. But one of the tricks I like with it is you can do what you can see with perf board, where instead of having to just try and make things work on these strips, you can join things around about and through different lines. So I quite like the idea of using that. And I like it being double-sided because it's mechanically stable for components, particularly when I'm going to build a variable frequency oscillator on it. Downside of using double-sided is trying to get the components back out. At times you've got to get the holes clear of solder if you've gone and put the wrong component in. Note to self. Right, let's move on to the next thing. So we've got a few to get through. Dead bug. What the heck is that? Or ugly construction. I showed you a little piece of board earlier, and to try and get away without waffling too much, just throw the transistor on the floor so we can't find it. And right, there's the board down. I have in my right hand a transistor. I've already preformed it with the leads facing outwards, and I could either glue that on, hold it with some blue tack, or chance my arm that I can connect to the components to it. But if I soldered that, if I used a bit of super glue to hold that in place while I put other components onto it, then I can construct that way. And if you look at the photos that I've shown, you can see where I've got like a resistor and a capacitor connected down, soldered down to the earth plane of 0 volts. And then I take it up to one of the leads of the semiconductor and solder them there. And that's the method that has been used throughout that particular little board. The advantage of building like this, no drilling, no preparation other than cleaning the board so that you can solder nice and cleanly on it. And as you can see underneath, there is a photo of a little active amplifier I built for HF listening. That was a George Dobbs design, just runs with a little 9-volt battery, stick a piece of wire in the end of there. And it's absolutely ideal for casual listening. And casual would be the way that I listen these days, with my hearing. A little bit further on, I was sent this photo by a friend of mine to show how far you can actually take this type of construction, almost to what we would have probably called years ago, almost a rat's nest. What is incredible about what he's built there is I know he switched it back on and it still works. But the idea of taking that up a mountaintop is probably not a good idea. But the point being, it's very quick and easy. And if you get it all to hold together, it's amazing how well some of these things can work. Another one which came my way was something which I called old development board. But a certain gentleman here this evening has told me it used to have a name of blob board. And during lockdown, I had a few of these pieces of board and decided to use this to build simple things on there. I realized I could fit ICs, maybe 16-pin dual inline ICs, onto these boards. Or in one case of which I've actually shown you, that's actually a direct conversion receiver. And I've actually got 4 8-pin DIL ICs on there and just wired everything else around it. And it works remarkably well. These boards have been around many, many years. I should think probably the 70s is my best guess. But the incredible thing is I still see them turn up at some of the radio rallies. And it's just a simple way. You haven't got a drill. You just find ways of soldering down either ICs or sockets, as you can see in that actual photo. Again, it's probably limited just how much RF you can put on these boards. These are for low voltage, low wattage projects running with about 12 volts. The idea of putting much more on there, I wouldn't. Right, more construction methods. Let's go back again to the simple copper clad board. And one gentleman many years ago just came up with a very simple way of running a hacksaw across both ways, across the actual board, and making these grids and then soldering components directly into those grids. And it's a very cost-effective way of making a very simple circuit board. Next, moving it on a little bit, is still using this board, is actually using these things on here, which are little pads. And the upper of the three photos I've just shown you is an IF amplifier I built to test some MOSFETs after I'd blown a couple up for the first time in my life. I had to prove whether or not I knew what I was doing. Now, the idea of this construction is you use a bit of super glue on the back is the best way that I find of doing it, but I use industrial super glue. Clean the board again. It's important because otherwise even the best super glue will have fun. And you just use a sparing amount of super glue to do it. Reasons being is one, it'll just squodge all over the place, and two, you do not want to get your soldering iron in dried super glue. It's not good for you. So I put these pads wherever required to make a circuit. So you can choose where you just take one of these pads off and put it down on the board. And I use a particular pair of tweezers, which are flat, to place it. Just hold it, take the tweezers away with a bit of luck that I haven't actually glued them down as well. And then in the bottom left-hand corner, there is actually a photo of a 1-watt transmitter for 30 meters that was built using this method. I promise you there are pads there, it's just they don't show up very well, but that is the method that I used to build. This works as the ground plane. You put these as I say, as pads wherever you need to put connection, and then solder other components down to the ground plane. A posh way of doing it, again with the copper clad board, is to actually make islands. And it's a really tidy little technique. It really does look quite posh, doesn't it? I haven't actually got this tool myself, but I do like that technique. Again, you can just drill them anywhere, but there is a big proviso. You can't do that with a hand drill. A drill stand is required. You put that in a hand drill and you're going to find quite a nice piece of artistic work. Right, on to some more. Right, breadboard. Again, I think this very much with the advent of the ICs back in the 60s and 70s, and it's been used ever since for a lot of development. I've got my own little board here, which I'll show you in a minute. Now, this board, again, was never built for RF, but has been used numerous times. It was built for logic ICs, audio ICs, just that type of stuff. One of the reasons being is, I think if I use that strip board, if I can just go back to it a minute. Behind these rows, well, first of all, let me step back a minute. Straight down the middle of the one to the right, the photo to the right, you can see there's a channel. And the idea is that you just straddle this channel with an IC, one lot of pins one side, one lot of pins the other side. And then you have rows of connections that you can make to each one of those pins. And I'll just say what I mean about rows is just like on this board, underneath there are these 5 connections, and they're sprung contacts. So there's 5 of them along there, then another row of 5, etc., etc. The reason it's not very good for RF is because there's some real capacitance between those rows of metal. So that doesn't stop people building with it either, does it? And I've managed to pull this out from an article which I did many moons ago. And this is a 40-meter direct conversion receiver. And again, it was built very much in the way that George Dobbs built many years ago. Just 2 ICs on there. You may just about see 2 ICs actually straddling in the middle, just down there. That, like I said, on that board. and then you just connect whatever else is required onto it. That worked perfectly okay. It received sideband and CW signals on 40 meters. And then, not to outdo myself anymore, I decided to build a complete transmitter receiver on a board for 40 meters. And that runs 1 watt, just under 1 watt out on 40 meters. It tunes about 6 to 8 kilohertz. The receivers, it works. It's even got what we call semi-break-in. You hit the Morse key and it'll go over to transmit. There's a speaker on there. And I talked to somebody on 40 with it in Poland. So I was absolutely delighted that you could be as silly as that and it works. I'm not the first person to do it. Plenty of others have messed about like that. One of the problems you have with it is, of course, components can fall out. So you do have to be a little bit careful with it. But I'll tell you a story about that possibly another time. Even more construction methods. I wanted to step back a little bit in the amount of construction, because really when I first started back in 1840 or whenever it was building simple things. And I just loved this little project that was put together by Mike, G4EJB, in the GQRP magazine brand. It's just a toroid, some wire, capacitor, SO239 connector, a wing nut and bolt, etc. So there's a bit of drilling and very little work. But what do you finish up with? A rather useful 49 to 1 unbalanced to unbalanced balun, or whatever you want to call it. Very little work required. And I just thought that's absolutely fantastic as a starting point for someone in construction. Build something like that and you go, yeah, that's where a lot of us would have started. Something simple. I would have started probably with simple things like toggle switches, trying to switch antennas until I realized that they weren't particularly the best thing to do such a thing with. Going to the other extreme, something of which I thought was really something else as far as construction was concerned, was the modular approach. There are so many modules available these days. The idea that you can actually build something as complex as this without having to go down to component level is fantastic. And that was put together by Giles Reed, sadly no longer with us, but I really did rate this as a project where you've put in 70 centimeters and then you're talking on the QO100 satellite. I really do rate that as a project. It's a little bit of soldering, I believe, involved, but very, very little. The rest of it is just connected all together. Absolutely fantastic project. More details of that will be shown at the end. Yeah, we're going to have some more. Right, we're now going into some of the things that make me smile. I never thought I'd see a chopping board being used to build a 23 centimeter antenna. Now, yes, there is some electronics behind there, bolted up the back, but I just had to smile when I saw what Peter Parker had come up with. And he showed the results he'd got with it, these simple antennas he'd built using a chopping board. I thought, there's no stopping this guy. Some of the stuff that he's built is really quite remarkable. Something we'll step back in time to where I probably started, which was actually with valve type technology. This stuff is not for beginners because there are at times very lethal voltages involved. Some of the parts are getting difficult to get hold of, but still a number of people still like building with valves even to this day. And you use these things called tag strip, which just space components off from the metalwork. I purposely took this picture to show you the mains transformer, because that's where lethal voltages start and can then go into other parts of the circuitry as well. So as I say, not for beginners, but still really good fun to build. And then I thought, after seeing Peter's chopping board, I'll just show you one little transmitter receiver, that 30-meter one that I built into a tablet box. I always like to mention it's always got a very clean signal. Round of applause, thank you. Right, that's all I'm going to do on construction. relieved. You've built it, but it doesn't work as it should. Did you check your handiwork before you switched it on? These are questions I do have to ask myself, I promise you. I said in particular, like with strip board, it's so easy to have missed where you didn't break a track or drilled a little track out. And I will mention about drilling the track out at that point before I do forget completely. Don't use a hand drill to drill out strip board because you'll go straight through. So I just use a simple little hand drill and just use that by hand to take enough of the copper out to break the track. So check your handiwork first. In fact, what I would say to anybody is whatever you've built, put it down, go away from it and come back and look again. Because it's a bit like even writing. You just become so familiar with what you've done, you can't see what you've done for the looking. So go back and look again with a fresh pair of eyes. As I say, looking is so, so important. And as one gentleman over at Grantham pointed out, is take photos. I mean, I brought along tonight a magnifier. That's what I've been using. I've even got a bench magnifier as well. But he said, why not take photos? And there are a couple of photos of the back of a board of which I was given to look at. And we'll have a little look in a minute about what we can actually see on there. And this is a big one here. Kits, did you really follow all the instructions? Well, here I am. I've been building all these years. And I go to a convention back in September, and we build a transmitter. Some excellent instructions. Did this person follow them? Absolutely. A good method with instructions is to tick off each step done. I didn't do that. I could just got a few components. Yeah, I can do that. Cut a wrong lead off a coil and then thought, hang on a minute, I've got something missing here. Hence the reason why. Tick every step off. And I did an article for Basics a few weeks ago. And just so that you can actually see, I really did, hopefully. You might just see I actually have ticked off the components when they've been fitted. And another good thing is, even if you have made a mistake, you can go and put a line back through the tick. It's simple things like that that will just give you a method with construction. And another thing I'll come back to is when you've built, it's very easy to have miswired, like with the perf board that we showed earlier. You've just connected something up to the wrong place. So have you really built it as per the circuit? So you've got to really be able to go back and look and say, is that component there connected to that component there? So do check it thoroughly. I said I'd just bring these up for you to look at. I'm not going to leave them up to the screen too long, but it's just to show you one or two things about soldering, about how things can actually work. And they did work, but may over a long term fail. Some of the things you may see in the right hand photo enlarged, on the right hand side of it is the cropping of the wire that could have gone over into the track next to it if it had been pushed down onto there and caused a short where you didn't want one. Other things can be that a pin just is not soldered quite enough, or a wire coming through a board. So it's just looking round and saying, right, can that be done a little bit better, or whatever. In this case, I think there wasn't enough heat applied to solder on this particular board. Never mind, doesn't matter. Right, so where to start? What do you need beyond what we've just discussed? I put this up on the screen to remind myself, a simple appreciation, a method for testing circuitry to find basic faults, and combined an understanding and a method will save you time. A modest outlay of a multimeter, it will go a long, long way. And that multimeter is still with me today. All right, and just see what I've put up on the screen. It had a 3-year warranty. I think it cost me less than £10 at the time. The reason I bought it was the meters that I'd been using up until then were even cheaper than that. And quite honestly, they're very basic and they worried me when you came to using them on higher voltages. This one actually has got TUV rating on there, and I take that a little bit more seriously. Having used professional equipment for a simple DIY meter, this isn't bad, but it obviously is not the same as the meters costing a lot more money. It's robust. It's still got a lot of ranges on it. You can buy what they call auto ranging, which simplifies things again for you. Let's have a look at the measurements that can be made. Resistance and continuity. I'll say it even properly now. Those are very useful tests, and the DC voltage. We're going to be using those in some of the testing in a while. And again, you can see on here, this will do current, both AC and DC. And again, AC voltage as well, up to 250 volts. The terminals for the test leads. This is where you do need to become familiar with it. And this is a very good point that I brought up at one talk. Take care to connect test leads to the correct terminals. Just imagine that you have just connected to measure current, and you want to measure, say, about 1.5 amps current flowing in a piece of circuitry. That's going to require you, if you've got a meter like this one, to actually connect to the 10 amp connect terminal there. And I would then put that on, show off, know what I'm doing, onto the 10 amp range. Now, measure my current, measured 1.2 amps, and I said now I want to check a voltage. The first thing I'm going to do is I want to put it back to voltage. Put that to voltage and bring that round to 20 volts there. If I'd have left it connected in that 10 amp socket there, between the common and 10 amp is what's basically a very large shunt for the current. It looks like a short circuit. So if you'd have put that across as a voltage measurement, it would have been a short circuit. Could have blown a power supply up, a battery, which could have been even worse, or do damage to circuitry. So it's just learn to connect. So that's the first thing that I do with a meter like this. Not all of them do this, but if you have got one, learn again, just the discipline of going, right, that's current, high current in particular, lower current, but when you go back to voltage, it's got to go in there, okay? You may blow a fuse in this, but you may do a lot more damage. Looking at a look at voltage measurement. Voltmeter has very high resistance, so it doesn't load a circuit. Digital multimeters, very, very high resistance indeed. This is something which I brought up for very good reason. Even though the voltmeter is shown above connected across the battery and load, 3 tests can be made. You're probably sat there going, really? I can only see one. I'm measuring a voltage across a battery and a load. With the DMM switched on, place the test probes on the battery or power supply terminals. This is 2 tests in one. You're going, really? Yeah, it is 2 tests. A meter reading says the multimeter is working, and the reading tells you the voltage. And you go, well, that's a little bit pedantic, isn't it? Well, the reason I say it is on my meter is a hold button. And if I press that button and it doesn't lock, or I've just nudged it with my hand, it may lock to whatever the reading was before. And if I try and put it across a voltage, it may say nothing. So I think, well, there's nothing there. Hence the reason why I say, first of all, prove the meter's actually working. The reading then tells you the voltage. I've then written on here about place the test probes on the load supply terminals. That voltage reading should be similar. The reason I say this is many moons ago I was working on emergency service vehicles, The radio itself was fitted in the boot of the vehicle. I'm not breaking any no secret acts at this point. The radio was fitted in the boot of the vehicle, and it was actually powered by the battery under the bonnet. So that meant there was a very long run of cable from the battery to the actual radio itself. Inside the car was what was called the control unit that obviously controlled the radio. And that was also going back to the radio in the boot. When this radio was put on transmit, it's obviously drawing quite a lot more current than it would be if it was on receive. And the radio would stop working. So we measured the voltage actually at the radio in the boot. And from what was measured at the front to what was measured at the back was something like 1.2 volts. What we did to overcome this was to actually put a higher rated cable in, so there was less voltage drop because of the resistive loss of the cable. But if you consider what we were really up against with these vehicles, was this battery was not only powering a radio on transmit, it was also doing lights and various other facilities bolted onto the car. So you can imagine that battery was taking quite a hammering in use. So it really taught us to be mindful of terminal voltage on batteries and the condition. And as a few of you probably well know, that battery voltage can be low and still start a vehicle. But as I say, when it goes low and you start putting more loads on there, this transmitter actually stopped working, and we overcame it with a heavier gauge cable. So hence the reason why there's an example of measuring voltage at both ends. You won't need to do this with a simple board in theory, but it's just to give you an idea of why I say what I say. Now we're going to start getting technical. Two resistors. Right, we've got a 2K and a 10K resistor, 2000 ohms or 10,000 ohms connected in series. There's a 12 volt supply, the positive to the top and the 0 or the minus to the bottom. And I've chosen this as a very simple example, not because I want to blind people with mathematics at all, but the type of fault finding that we're going to talk about is more about concept and expectation. And I don't want someone to have to reach to a calculator. So these were chosen to just show a very simple example. If I say to you this, what voltage with respect to 0 volts do you expect to measure at the junction of the two resistors? It's very quiet, not getting too many answers. Well, point being, before I give the answer, just look, there's a bit of a ratio here. We've got 2 there, 10 there, 12 parts. So with a resistor, the smaller resistor, you're going to be looking at least voltage drop across the 2000 ohm resistor. And I would guess, wouldn't you, you would get 10 volts. It doesn't say 10 volts. Why doesn't it say 10 volts? It says 9.93. So there are reasons for this. It's down to tolerance. One, I've said to you that this multimeter I'm using is not a professional meter. It's going to have tolerance, okay? It's going to give you a reading close to, okay? The next thing is that the components tolerance. They may not quite be 2000 ohms or 10,000 ohms. That could explain 2 reasons why that voltage is quite right. There's nothing, that's the first point, there's nothing wrong. That is roughly what I'd expect to see, okay? It's near enough 10 volts. So there's no rip those resistors out or throw away your meter. Even with a high quality meter, you're not necessarily going to see the right voltage. Why? Did I actually say to you we have 12 volts to prove it was 12 volts to start with? It could have been 11.9 something, couldn't it? So it's to give you an appreciation. Now, I was getting a bit excited then. We'll move on to the next step. If the circuit was now inverted, And if you notice, the 10k resistor is now at the top and the 2k resistor at the bottom. What voltage would you expect now? Well done, you've caught on. Very good. 2 volts. They are measured at 1.97. And for exactly the same reasons we've mentioned in the previous example, that voltage isn't quite what it is, but it gives you an appreciation. And you're going to wonder, why have I gone to all this trouble? Right. There you are. That's a disclaimer. Moving on. I'm now going to add a diode and another resistor to that 10k and the 2k. There are now multiple current paths. And I've asked a question of what components are in parallel. Now, if you look at this, we've got a diode and a resistor RX in series, but they are actually in parallel with the 2000 ohm resistor. Current will actually be pulled through both of those branches in that circuit. So what do you think could be the net result if now more current is going to be pulled through the 10,000 ohm resistor? What's going to be the net result to the voltage reading at that junction of the resistors and the diode? It's actually lower than what we had previously. We had about 2 volts when we just had the 10k and the 2k, but now we're drawing more current with that diode and resistor in parallel with the 2k. So you've now got an appreciation. It's going more than one way, therefore it's going to be lower than what we saw with just the one resistor. Next question. No, I'm not going to tell you. I'm going to ask about the voltage at the junction of the diode and the resistor. And one astute gentleman turned around to me. He said it depends on the type of diode. He's absolutely right. I'm going to tell you it is a silicon diode. And a silicon diode will have the voltage drop of what, 0.6, 0.7 of a volt. So when I go to measure that junction of the diode and the RX, I expect it to be lower than that 1.29. Sure enough, when I measured it, it was 0.71 of a volt. That just shows me it's all working, doesn't it? All right, good. Why did I go through all of this? Well, I just wanted to get as far as a simple amplifier. And if you look at this circuit, we've got the 10K, the 2K, and we've actually got one of the elements of a transistor involved, and the RX resistor has been replaced by 150 ohms, and we've now got connected the collector of a transistor and a resistor in the collector. The arrows, the red arrows, here sometimes, just show again current flow within a circuit. And that's just to give an appreciation. The 10K and the 2K are just there to set, if you want, the bias point of that transistor amplifier. When I say it's an amplifier, I haven't put any means of connecting to it, either an input or an output. I've only shown the DC components because that's all I'm interested in as far as fault finding is concerned this evening. All right. So you can see an idea of current flow. I've tried to draw the arrows to give you an idea where all the currents go and add up. The base collector current makes the emitter current. Okay, that's how one of these simple transistors work. That's enough about that. Let's have a little look what I've got next, remind myself. I've gone and measured 1.89 volts this time at that junction because it's slightly different with that transistor than a diode and that resistor in the previous example. So that's the voltage I've got there. You got any idea what the voltage might be at the emitter? Around about 0.7 of a volt lower than the base. So 1.16 is what I measured. And with this circuit set up like this with this transistor, I've got about 6.74 volts on the collector. This is what is called a Class A amplifier. As I say, there's no capacitors showing that would either couple an input or couple an output. No bypass capacitor to sort out whatever amplification we wanted. It's just a very simple analogy of the DC voltages that you would find within an amplifier. All right. You're going to see that with every amplifier? No. You're going to see it with every, if I built another one with another transistor, would it be exactly the same? No. This is just to give an example, an appreciation of what you will find when you're actually looking at circuitry. The idea is it's about that there. It's going to be about 0.6 volt, 0.7 volt lower. Let's just make certain that looks about right on the collector. But what is happening if these are not present? Let's have a look if there was 0 volts. If you went to measure the base of the transistor or the junction of those two resistors, and there was 0 volts there, either a short circuit or an open circuit. For 0 volts, the short circuit would be between the 2000 ohms and earth. And if you were building with strip board, that's a typical type of thing that you could find. There's a piece of solder gone between the two tracks, and that 2000 ohm resistor is shorted out. It could be that a solder joint hasn't been made onto the 10,000 ohms, therefore there is no way the current can get down there, and you see the voltage on the base. So that's what I mean about the short circuit and open circuit. Remember to select a suitable resistance range on the DMM. Good point, Lee. I must remember that one myself. If I'm looking for a short circuit, I'm going to use a low resistance reading. If I'm looking for 10,000 ohms, then I'm going to be using one above 10,000 ohms. All right? Because again, you can very easily put it on the wrong range and go, what am I looking at? How do I know? I've done all these things, hence the reason why I can write about them. Again, another one. There's no voltage on the collector. What could be causing that? Open circuit. It could be that the 680 ohm resistor is not connected to solder, isn't made. The idea of these components are faulty, particularly resistors, particularly if they're new. It's very, very rare to have failure of resistors. But, you know, once in a blue moon, you will find something, but really, I've not seen many of them. So the 680 ohm resistor to 12 volts could be open circuit. And then it says check transistor lead can for a short circuit. That could be another reason. It could, if the transistor has got a metal can, it could be touching down to the earth plane for some reason, or the lead could be touching down. So that's the reason for a short circuit. Another reason could be, I might just be able to show you this. I hadn't thought of this one before. On this actual little transmitter I've built, thank you very much. Let me just turn it around there. There is a transistor sat on a heat sink. The transistor, in this case, I think is perfectly, it is actually insulated from there. So there is an insulator behind it, and there's also a little plastic ferrule of which the bolt goes through. And it won't be the first time that I have seen a bolt go through, catch the side of the ferrule, and actually short the tab of a transistor to the metal can, which goes down to 0 volts. That is a classic one from the past. Finally, 0 volts short on short circuit and open circuit. Short circuit again could be 150 ohms, actually down to the 0 volt rail. The open circuit again, is the emitter soldered or is the transistor okay? All right. And this is a very important point, and I left it to the end. All resistances are checked with the supply removed. If you try doing this with 12 volts applied, you will get some very silly readings indeed. So the point is, you've got to remove the supply, and if you do find silly readings, just put your meter on voltage and actually see if there is any voltage still there. It could be capacitors, charge, etc. But this is a standard way that I would have tested a very simple amplifier. But as I say, just mindful that you've got the supply off when you do this, because that voltage will impact heavily on the resistance readings that you get. And as I said early on, these are good examples of possible strip board faults where tracks have joined or wires just actually got in between, etc. You found the reason for 0 volts at the junction of the 10K and the 2K, and that's all now working okay. And the voltage, the base emitter, appeared to be similar to what you expected. If you remember back in the example, it's about 1.8 volts and 1.2 volts on the emitter. But the collector is 12 volts. Why is that? Well, again, it could still be there's a short on the 680 ohm resistor. 12 volts going straight on the collector, or the open circuit is the transistor. Could be open circuit, or the actual collector lead isn't soldered 100%. And there's a clever little trick to give a demonstration of it, but sadly, you can use your multimeter on resistance applied to be able to, that is still a transistor. Back to a diode, if you put a multimeter on resistance and check across a diode, one way you will see low resistance, turn your lead around, you will see a high. You can do the same with a transistor to a degree, and the idea I have behind that is this in circuit, you can go, yeah, I've got one reading that way, change the leads around, got a different reading that way. So it's still something of a transistor. It's not foolproof, but it's as simple, because sadly you can get voltage breakdown that can cause faults that won't be picked up. Oh, we've got that far. We've got as far as something a little bit more. Block diagram fault finding. And I am indebted back probably 45 years ago to a gentleman by the name of Canoe, who taught me the method of fault finding like this. We've looked, as far as we're going to this evening, at fault finding to component level. But just say you've built something like I have in the past number of times, a direct conversion receiver. It consists of 3 fundamental stages: audio amplification, a product detector, and an oscillator. And you build a direct conversion receiver and nothing appears to come out of the speaker. All right, so where do we start trying to work out where the fault is? Which stage could it be in? This method of working out where faults are is, if you want the fundamentals, to far more complex equipment and also into systems as well. You start to understand where to look first to have a method to locate a fault. Step 1, audio output. Is there something coming out of a speaker? Right, we've proved we've got 12 volts on, and some of the basic tests we've already done onto the actual board you've built. How can we prove if there's audio output? Well, first of all, you've got a speaker. Hopefully you know it's a working speaker and it looks like it's connected up. Let's just assume that is the case. The audio amplifier, you may have a little audio oscillator that you can actually put at the input of the audio amplifier and be able to prove whether a signal goes through there. If you haven't got a simple audio amplifier and you're running with low voltage, you can put your finger on the input to an audio amplifier and you may well pick up hum or extraneous noises like that. And that says the audio amplifier is probably working. If there's a volume control on there, go back before the volume control to prove that signal is going through from the volume control right through the audio amplifier. Right, so that's working. The next stage is have a look to see if the oscillator is working. Now, I don't have fancy test equipment. I could check an a frequency oscillator is actually working a few ways. I've got a very old scope which will show me a waveform. What it won't tell me very easily is if it's the right frequency. How can I tell it's the right frequency? Well, with a direct conversion receiver, the oscillator is running at signal frequency. So if it was on 80 meters, I tune another receiver to 80 meters and see if I can hear this oscillator. That tells me it is on the right frequency, in theory. So if you have got a scope, great. You may see something of a reading on some DMMs, some multimeters, but I would say to you, another way of doing it is, if you know where the oscillator output is if you just put a screwdriver on the oscillator output and it increases on the receiver you're listening to, then you've just put an aerial on the oscillator and that's picked up more signal from it. So then you know an oscillator is actually working to some degree. Now this is the big point. You are now going to use steps 1 and 2 to be able to prove it's the detector that we're going to check next, because we know we've got an oscillator into it. We know we've got some way of actually hearing an output from the detector. So it's a very cunning way of doing very simple things, using different parts of the circuit to be able to prove, I'm going to look there. You didn't connect an aerial up. Was that all the fault was? Who knows? But all I'm trying to get at is you're now finding ways of being able to go from one stage to another and then go, right, I know those two are going, that's the one I'm going to go to next. You'll be pleased to know we've got to the end of fault finding, apart from the continual fault finding that I have been married for over 40 years, but we weren't going to cover that one this evening. Always remember the basics. It's so easy to jump in the deep end when trying to find faults. If you have just turned around and done things like look that you've got good lighting, and as I say, if you use a camera to take pictures or magnifier or whatever, that is the one that's going to save you so much time. Circuit diagrams, it won't be the first time that I've actually had a board given to me, but the circuit is of a different generation and things have been modified. So you do have to make certain it's the right issue if you wish, and just go back and use that circuit diagram to go, yeah, that is connected there, yeah, that's there. That is going to give you the familiarity. Method and expectation. I hope you've seen enough simple methods, and as I say, what to expect. That is so helpful. If you can go in there going, this is what I would expect to see. All right? It just means you've got ideas, things that if you want in the toolbox to be able to throw at it. And you do your measurements, and some of the trip ups are with your measurements. And as I say, just keep having ideas of how to throw possible answers at what's not happening. So I hope that has been of help. I think I'm probably going to have a lie down at some point. Just a few things I'll show you that I have built over the years, in various guises. I think the one that stands out most or makes me smile the most is the 40 meter little 1 watt CW transmitter receiver. But I also liked the 15 CW transceiver because I really fancy display to show up through. It really cheered me up. And the whisper transmitter is built in a mod. The little 160 meter transceiver, the case, engineered flooring tiles, because I've nothing built it. And that was the 40 meter transceiver was resurrecting a project that a friend of mine had actually given me from years ago and throwing it into a box to actually work. A few acknowledgements to a few people for all their help this evening. I'd like to thank all of them. And as I say, you can see where I started and a few others did, as with the Philips Electronic Engineers Kit. That was quite an amazing little box of tricks all those years ago. What I do think is really good these days is you've got these snap together boards, which are a great place for people just to start with electronics if they so desire. But this was very much that of its day. And the fun that you had with building these things with little bits of cardboard and metal springs was absolutely fantastic. Thank you to all those people for their contribution towards what you've seen tonight. And here to find out a little bit more. I'll leave these details on the screen, and I'd really like to thank David and Tammy for all their help this evening. Over to you.
Thank you very much, Lee. I have to start by just endorsing that final slide, or penultimate slide, because the Philips electronic kit also helped me enormously. I remember Mum and Dad buying me that on one holiday, which sounds like a strange thing to take on holiday, but that was the sort of kid I was, and making that. And I think, although the snap together kits are great, and we use them in our radio club to show at public demonstrations, particularly Science Day coming up, we'll be using it again. My only criticism is they've sanitized the component itself rather, haven't they? Because they fully encapsulate it, and often you don't even see the actual electronic component. Whereas those Philips electronic kits, you use the raw components to fit under springs. I don't know if you agree with that, Lee.
Yeah, I do. You're absolutely right.
But anyway, they're all good because they encourage people to understand, particularly young people, to understand what goes into electronics nowadays. Anyway, I hope this has been an inspiring talk for you. It has certainly for me. And if you've got any questions or comments and you'd like to share them and you haven't done so already, please do it now on YouTube chat or BATC messaging, and I'll read as many as I can to Lee as well. And don't forget to include your first name and your call sign within every message if you can. Please, thanks very much. We have got several messages, Lee, so I hope you've managed to grab a drink. I hope you haven't had a lie down yet. Please don't do that. Just give us a bit of time. Now, the first question which came up, I'm going to I'll read it to you because you're the presenter here, but I think I can help with a solution. But I'll read it to you anyway. I think the first question, well, Stuart Henderson actually said, GM5 DNA, I found the Pinecil soldering iron to be excellent. That's PINECIL, not heard of that one. I guess a play on the word pencil. But anyway, that's a brand that Stuart has found very good when you were talking about soldering irons at the beginning.
Yeah, all right. Okay.
Keith Lockstone, who's M0KIL, says you can't hang scope probes on surface mount components. And this is where I think I can help with a very quickly put together demo, but I'll hand it to you for what your comments are on that first.
It's a long time ago since I've even done it. I mean, you're absolutely right. What have I done in the past? I mean, I just use the prod simply onto surface mount components. What would you say, David?
Well, it's just one of those things that happens to have happened. At last year's wonderful Ham Fest at Newark, the National Ham Fest, there was a company they're displaying called Telonic, and they displayed some wonderful gadgets for doing just this. Brilliant. And I must admit I bought them, and much to my embarrassment now, my wife Tammy, who's the director on this programme, tonight rushed around the building here to get them together because they were still in their box and not being used. How often have you heard that before? But we've managed to put together, in the time you've been talking, a very quick demonstration of it because it is relevant, and it is a very relevant point that to measure points on small circuit boards, highly dense circuit boards with ICs, it's very difficult. But I found this gadget, and Tammy's now going to put to a little quick camera setup we have. So this is our little setup here. This is called PCB ITE or PC Byte, I guess. In fact, you can just about see it maybe on there if you can just see it on my finger. I said a firm called Telonic was selling it. And what it is, I don't know if we can see on here, these are magnetic pieces of equipment that just fit and sit on this metal plate that they give you in the kit, the starter kit. These are, again, magnetic mounts which allow you to mount the circuit board really rigidly but temporarily. So you've got spring-loaded connections here to sort of mount the circuit board. Can you see how they work? You may not have seen these before, but they are wonderful. I don't really need that third one. I wouldn't be any good on Blue Peter, would I? Anyway, this is the probe. This is the scope probe, and I thought exactly what Keith said, and it does work. So if I show you this probe before I use it, and we're going to get close up to this surface mount circuit board, this scope probe here, this actually screws in. And remember, this is all on effectively, this is a gooseneck, you know, the sort of thing you get on a big light, but in a miniature version. So this here is a gooseneck, and this is a scope probe fitted into a circuit board, and this here is a tiny sprung-loaded pin. Good job of cleaning my fingernails, isn't it? You should always do that for television. Anyway, and let me show you how it works, because the wonderful thing about it that's actually very hard to get over, even on TV, is how nice and light this is, because I don't know if you can pull back a little bit, Tammy, on the zoom. I want to show how this gooseneck is actually taking most of the weight. So this is just a tiny bit of weighted spring, and I can put it on a small surface mount. Let's go on the end of this tack switch here. And if you see, if I let it go, can you see gently that pushing down, up and down? Yeah. Hopefully you can see it at home as well. It's a sprung-loaded pin. It's a brilliant bit of engineering. I have no interest in it commercially, so I think I can say that openly. It was seen at the, for me, at the Hamfest last year. And if you do surface mount electronics and you want to take measurements, this is a scope probe. I think about 50 or 60 pounds a scope probe is. So it's not cheap, but then a good scope probe is still quite a lot of money. And they do also, though, a pack of 4 individual normal probes for DC measuring and things as well. So I hope that's been of help. You can see Telonic advertise in RadCom. Most missions of RadCom, they advertise test equipment usually. But this is a piece of wonderful equipment they sell. I believe it's made in Sweden. But it's really beautiful design, obviously created by an engineer to solve this problem. Anyway, I'm sorry that's taking this things away from you, but I hope that's helped, Keith.
That's very good.
Okay, the next question though, linked to surface mount, is there any recommendations on practicing with surface mount components on boards? Perhaps are there kits just for surface mount? And that's GI0AZB.
I don't really know how I can answer that. I've not that much experience with surface mount kits, so any suggestions that you've got on that, David, I'd be more than willing to listen to myself.
Okay, well actually, firstly, there's a couple of people came back on YouTube chat. Chris M0YGH says Google surface mount device SMD practice kit. That's what SMD means, by the way. Or SMD is surface mount device and SMC is surface mount component. And then also Stan Holmes said practice on any old SMC boards in removing and replacing the same component. I've also seen on a lot of the Chinese websites and eBay and Amazon that you can get surface mount practice boards. I think if you type that in as well, you will find little kits for a few pounds, which just gives you a handful of resistors and capacitors and a circuit board to practice with. They do take fine soldering, as you said, a decent soldering iron, a relatively small tip, although maybe you'd agree, Lee, that a good hot iron is as important as a large tip or a lot of power anyway.
Too true.
So that's my little bit of contribution towards it, but this is your show. And I want to now read out a question by David Dessa. I don't have your call sign, Dave, sorry. Should we only be using lead-free solder these days?
How can I answer that when I know what I'm using? There are reasons why we are supposed to be using the lead-free. Very good, either health reasons, environmental reasons, or even if we're looking at the board being given to somebody else or sold to somebody else, because I believe we're not supposed to do things like that. So I can't tell you what type of solder I'm using, can I? Sorry.
Well, I mean, I think it's allowed to do. I mean, I'll go with you, Lee. I use and I recommend in our radio club as well, where we show construction using leaded solder because it does flow better. I think anybody would admit that it works better, and that lead-free solder, where you need certainly at least at the very minimum you need a higher temperature to heat it. But it's obviously has to be used now in nearly all commercial equipment. I think some aircraft, aviation and medical equipment may be exempt still. But most equipment now has to be made with lead-free solder. But as far as I know, it's completely legal to, certainly you can buy it legally and use it for your own home construction. I guess the one thing we'd suggest with any soldering is to make sure you've got good ventilation so that smoke from both solder and particularly flux can easily get away from you.
The other part is, David, is to do with the...
Oh, we've just lost Lee, and that's the first time that's ever happened. I'm very sorry about that. That's unfortunate. I think many of you will have noticed that Lee's internet was getting slightly worse at the end. Of course, a lot of people are streaming later in the day, and so Lee's internet will be shared with neighbours just like ours is. Maybe that's it. But Lee is back. Oh, good. You worried us a moment, Lee. I think we didn't. I didn't mention this to you, but I think I ought to mention it now that your internet was failing occasionally. We were losing the odd word, but it certainly didn't disappear like that.
All right. Okay, I'm going to have to pay the bill then.
Well, yes, but no, I'm sure it wasn't that. It's probably, as I just explained, to fill a bit of time, that it was the a lot of people on the internet, of course, a lot more at night than when we did our rehearsal earlier in the week. Anyway, where were we at? I think we were talking about solder, and I was just saying about having a good ventilation is important, isn't it?
Yeah. Oh, definitely, ventilation is important. The flux is an issue, as well as the fumes from the other thing that I'll mention is obviously good hygiene. Hands, because it is breaking up.
I'm struggling with your internet now, Lee. To be honest, I don't know. You said is good. Did you say good hygiene?
Yeah, I did with less. You know, a number of times I've seen people eating with lead solder. It's not a good idea.
No, definitely not.
So, yeah.
But I hope I'm right in saying I think it is still legal to use, and for certainly if you're beginners and you're not experienced and you haven't got a very, you've got an extra hot iron that you need for lead-free solder. It's better to use.
It is. I totally agree.
I hope
the reality of,
Sorry, Lee, it's just you're breaking up a little bit again.
I know.
I've got Michael Naylor who said, very good tip here. It may be worth asking your local amateur radio club if they will run a construction evening and even buy some test equipment. Excellent idea.
It is. I wish I'd said that myself. I'm very pleased you were paying attention that I didn't. I was going to say about soldering in particular, get some nights put on, get some people who have spent their time doing this type of work. They're more than willing to help you be able to, take it to a level where you feel competent. And like you say, construction nights, I think they're going to take off. I really do.
Yeah, I do really as well.
Yeah.
Actually, can we ought to remind people, I did say it briefly in my introduction, that you were in RadCom Basics. You were the editor of RadCom Basics for quite some time.
Yeah.
And I think we're going to try and now show you just a picture that, so if you're an RSGB member, this is a benefit that is included within your membership, and you can have a look at RadCom Basics, which comes out regularly. And I had a quick look at the one earlier, and I think we're going to put that on the screen any minute now. This is live, so if you are an RSGB member and you log in and you look for RadCom Basics, we'll give you a link in a minute. This is the sort of thing you can see, and Tammy is just flicking through these pages. They're virtual pages. It's not published as a printed magazine. It's one that you can look at conveniently. I think if we go to page 16, there we are, constructing a kit, which I thought was particularly useful and relevant to what you've been teaching tonight. So if you've watched this presentation and you'd like to know a bit more and you're an RSGB member, do head over to RadCom Basics, and we're now going to just put up that caption for you. This is where you can go to directly, but you'd say you do need to be an RSGB member and sign in to be able to see this. It's rsgb.org/radcom-basics. Really useful magazine. Let's go back to our feedback now tonight. If you've got any questions or feedback, this is the time to do it, because we're coming towards the end of our program now. Graham Bohr says, great presentation, Lee, and shows that these basic steps can help understand the fundamentals of equipment, and typical examples of an very old kit from a collection of what some would say was scrap, repaired by you, and on air, test confirmed. That's the Walford TCVR.
Is absolutely right. Thank you very much, Graham. It was a real pleasure to do that. To see these old radios resurrected is it's a real pleasure to do it, because why not give them a new lease of life and actually use them? Why not? There's a lot of stuff out there that could be reused.
Yeah, and I mean, it may be difficult to build, multi-100 watt rigs and things like that, but a lot of people enjoy QRP. I think you do, and I do. Yeah. But then there are some wonderful QRP commercial rigs, like something like the Icon one, but they are very expensive, the 705. But for a fraction of that price, for sort of £10 or £20, you can build a transceiver that's pretty darn good and can transmit several watts. The sort of thing QRP, QRP Labs, people like that. Yeah.
Well, there's a little 5-watt transmitter there that was built as the GQRP convention transmitter, 5-watt transmitter. Really straightforward, fantastic bit of work by the GQRP club team. As you can see, even the circuit board was made by the club chairman. We'll ask him another time where he drilled the holes, but it's really brilliant.
So that looks like those tracks were drawn on probably with a pen, were they?
Yeah.
A resistant. I remember doing that in my youth. Where we should explain that often it's done in a photographic process with a circuit board, but you can also used to be able to buy anyway, pens where the ink was etchant resistant, and so you could just take a bit of copper clad board and draw the tracks on there and then etch it.
There you go.
Wonderful. I've had a question from WECB 640. Sorry, I don't know your name. That's all I've got. Where is the ground reference point on the scope probe? I guess that was the scope probe I showed earlier, which we've moved out of the way now. But it actually has a little lead that you can plug in to the scope probe part and go onto the circuit board. We literally did this in the background while Lee was talking because I didn't know that question was going to come up. So forgive us that it wasn't a complete or rehearsed demonstration, but I hope you get the idea. Anyway, have a look at that. Again, it is called PC Byte. That's what the system is called. A couple of people have asked what it's called. Stuart DeHamin. What is your experience of using reusable SMD sockets to avoid soldering SMD components directly? Do you have any experience of that?
No, I do not. I am limited with what I do with SMD simply because my eyesight won't allow for it anymore. 20 years ago, I could have done it, but it's just too much. So no, I cannot answer. I'm not really sorry.
No, that's all right. Well, I don't feel I should be coming in, but this happens to be one presentation with a subject which I'm both really interested in and know a little bit about. There aren't many really SMD sockets because it doesn't generally work, in my experience, at least for surface mount. The circuit board that we showed earlier, actually, everything was soldered onto the board. I mean, I guess it's one disadvantage. One thing you can do, though, is you can buy carriers which take a surface mount chip with say 14 or 16 pins or more, and it takes those pins out to traditional pitch pins like the ones you were talking about earlier, 0.1 inch pitch pins, which of course those you can either plug into a conventional IC socket or solder into strip board or something like that. So that's the sort of thing I do. But I think most engineers would agree that still, if you can, experiment with leaded components, in other words conventional components, with wires on them, because it's so much easier to move things around. If you're doing it with surface mount, that's hard to change things, isn't it, at the last minute?
Yeah, it is. You're absolutely right. I have done some surface mount work, but as I say, you're absolutely right. With this stuff, you can actually still work with it to a large degree, can't you? And you're not going to need so many specialist tools. Marks out of 10 for people who do it. It's skilled work. As I say, my eyes won't allow for it, and I just decided there's a lot of these components still about, and there's a lot of things you can build still with them.
Yes, I think most components you can still get, certainly conventional, the sort of resistors, capacitors things you can certainly still get in wire form. Some of them, maybe the newer integrated circuits, they might be harder to get in surface mount. So Dave Odessa says, I still have a Deacon Dalo etch resist pen. I remember that, Dave.
Fantastic.
Yes,
Yeah,
I remember that name now. Thank you very much for that. And Stuart Hammond has come back and said SMD breakout boards. Yes, that's probably the proper name for it. So if you search for those, let me see who asked that question. Who asked that question now? I think that was... it's Stuart himself, actually. So he is aware of those sort of breakout boards that make experimenting with surface mount much easier. One other thing can we just talk about briefly is multimeters and things like that. You used your fairly low cost multimeter there. What do you think about analog meters, the ones with the sort of meter movement on them? Are they still relevant?
They do something. I've still got one analog meter, but it's a very cheap one. The damping meter is rather important, and being a very cheap meter, the damping, well, it's almost non-existent. I mean, years ago, you would have bought, most multimeters were analog, of course, that we could afford. And they have got some use, particularly if you're trying to peak circuits. If you're using something like the digital multimeters, some of them will have a poor sampling rate. You're trying to peak a voltage somewhere, and it's behind what you're doing. So you can spend a finite amount of time or even infinite amount of time just chasing what you're looking for. And an analog will possibly give you that smoothness to say, yep, that's the peak reading. Downside of them is accuracy, loading, also voltage, voltage wise. There's a lot of things you have to understand about using analog meters compared to digital. If you put an analog meter into some of the circuits and try to even measure a voltage, you may well find the voltage is completely different to what the digital multimeter shows.
Because the loading of the analog meter itself. Yeah, on a lot of them, it tells you how many kilo ohms per volt it puts as a load, doesn't it, on the circuit? Yeah. Well, I must admit, as a tip for me, and I do use both, mainly digital, but if I'm fault finding a circuit, for shorts or opens particularly, I find that I can see out of the corner of my eye a meter movement, a meter needle moving, whereas I can't do that with meter. But Stuart Hammond has come back and said, any recommendations for LCR meters, which stands for inductance, capacitance and resistance meters?
Well, I have to say, I have got an exceedingly cheap one from many miles away, which absolutely amazed me how well it worked. But the reality is, spend a few more pounds and you're going to get a far better piece of kit, of which will measure down to very small values. So I can't give you any specific names. As I say, the little thing that I bought was pounds, and I was shocked how well it worked from like 20 picofarads or 20 microhenries, how well it would actually work. It does something, but it's the accuracy, bit tongue-in-cheek. If I use very high tolerance components, you can just say, okay, it's out a little bit, but it gives me an idea. But if you want specific, spend a bit more money. There was a good range at one time, I think, shown in RadCom, was advertised at one time.
I think they're still available, actually. Are you thinking about Peak Design? Yeah, Peak are very good in my experience. Again, there's no commercial connection between either of us to them, but again, they showed at the Hamfest and they do advertise in RadCom, and they're a British firm, makes some really nice little meters, and they do an LCR meter, which is probably gives you a bit better accuracy than maybe some of the other cheaper things. But the key thing is, isn't it, is to get building. And I think to summarise now, really, I think we've covered most of the questions, by the way. Although Graham, G8WNC, says, hi, Adello Pen, my first 2-metre home-built transmitter from Practical Wireless used that. Must be 30 or 40 years ago. There we are.
Fantastic.
But I think to summarise, well, you summarise, please, Lee, getting people building?
Absolutely. It is. It's trying to say to people, there are others out there that will help you. We're trying to do whatever we can to get you to be able to enjoy this hobby. It's supposed to be fun, isn't it? And if we can do that, that's the best we can do with all the knowledge that is out there in all these clubs and within the society, is to be able to support you in your hobby.
Yeah, absolutely. And I think also encouraging younger people, if you can, to learn about construction. Otherwise, they're going to be taking for granted all those boxes that they buy and not understand what goes on inside them. And after all, even though technology is getting wonderful and clever now, we're still going to need engineers to design these things, aren't we?
Yep. Yeah.
Oh, I've got one other question. I will try and read that to you. This will be the final question. Do people still use GDOs still for radio work? We should explain what a GDO is first. I'll let you do that.
A grid dip oscillator, good grief. I haven't got a grid dip oscillator. I've got a FET dip oscillator. I haven't got actually the valve version of it, but it's a means of being able to do something like check the resonance of a piece of wire, of an antenna, of a coil, of a tuned circuit. It's a very useful device at times, or it certainly has been in the past. I used one probably about 5 or 6 years ago just to trim an antenna wire to the right length. So some people still do, but obviously analyzers have come along now for silly money that will do amazing jobs. So you take your pick. If you've got one, it's still got some use, is my answer to it.
Yeah, and have a look at your local radio rallies in the summer, I think. Yeah. They'll probably have them as well. Lee, it's been a wonderful journey. Thank you ever so much for tonight. I'm sure, and I hope and sure that we've inspired many to give construction a go and to spread the word. Thank you ever so much for tonight.
Pleasure. Absolute pleasure. Thank you.
Thank you. There we are, and that concludes this webinar. And our thanks again to Lee Aldridge, G4EJB, as well as the team who put this series together behind the scenes. Well, we hope you've enjoyed this Tonight at 8. Why not give us a thumbs up like on YouTube if you did. We hope that you will be able to join us next time when we'll be looking at Antipodean antenna adventures with Bob Bauer, GM4DLG. Now, tonight's webinar was all about construction, and if this has inspired you to make something, then there's just time for you to enter the RSGB's construction competition, which closes on March the 1st. There are a wide range of categories, including one for beginners and a new one for designing a project which could be used for outreach in a school or public environment. For full details, please see the special webpage at rsgb.org/construction-competition. And if you'd like to see details of future webinars or watch recordings of previous programs in this series, please visit us at rsgb.org/webinars, where you can also send us comments and feedback. And if you subscribe to the RSGB's YouTube channel, you'll be notified of all upcoming Tonight at 8 webinars, as well as other new videos and presentations from the Society on a wide range of amateur radio topics. Thank you for joining us this evening, and until next time, this is David G7URP signing off and clear. Bye-bye.